So welcome students. In this lecture, we are going to study about solving PDEs using Frank-Nicholson method. My name is Vincent Nando. I'm teaching at Dexter University. So we are going to begin from derivation of the Frank-Nicholson scheme for solving hyperbolic equations. And then from that one, next lecture will be giving an example on how to solve hyperbolic PD using Frank-Nicholson method. So this is how hyperbolic equation looks like. This is same as the wave equation. So let's derive the scheme for solving this. So consider derivation of Nicholson-Crank's method for solving hyperbolic PDE. The example that we're going to take is an example of a wave equation. So consider the wave equation partial squared u partial t squared equals to c squared partial squared u partial x squared, where x lies between 0 and a, and t lies between 0 and b. So I'll call this one equation 1 with the initial conditions u of 0t given by a function f of t and u at at, so initial and boundary conditions. U of t given by function g of t, and then u at x0 given by a function phi of x, and partial u partial t at x0 given by a function psi of x. So let's call this one 2. So to solve the scheme, to solve the equation, question 1, together with the initial conditions, with boundary conditions and initial conditions given in 2, we take the rectangular x t axis. That means that on the x-axis, on the horizontal axis, we have x, and then on y-axis, we have t. On the vertical axis, we have t. And then this is step 1. Step 2, we divide the interval zero to a into n equal subintervals. So let's give these ones a, b, so that you don't confuse with the labeling of the equations. So let's call this one step a, this one step b, and c. We divide. So remember, this along the horizontal axis, this is the x-axis, and then we divide the interval zero b into m equal subintervals. So this, remember, is along the t-axis. This is the horizontal axis, and then this is the vertical axis. And then, so therefore, the distance, this distance between two consecutive values or coordinates on the x-axis is, so this small change in x, or the change in x, is h, while that on the vertical axis, on the t-axis, is called k. So each step on the vertical axis is k, on the horizontal axis is h. So therefore, we obtain a region in form of a grid as shown below. So with this division or partition of the region, so this is what we have. So we have so this is the x, and then this is the t axis. So we have so we show that the intervals are equal. And then we have this vertical, So this value here, so this is what we call the T naught. This is the T1. This is the T2. etc up to this is Tj, and then this is Tj minus 1, and then this is Tj plus 1, and then up to the last one is called T sub m. And then on the horizontal axis, we have x naught, x1, x2, up to we have this is xi, this is xi minus 1, this is xi plus 1, and then you continue up to the last one is x sub n. So this will be xn minus 1 etc. So these are the regions we have. So in this diagram, you see that we have the intersection, these nodes. So the objective of all the process is to find the values of the displacement or the values of x are these given nodes. So this is what we have. So in this grid, so because these things are assumed to be uniform, so therefore the central difference from our numerical class, the central difference formulas for the partial differential equations for the second order partial differential equations or partial derivatives in equation 1, which define the wave equation, are approximated by, so this from our numerical class work, partial squared u partial x squared is approximately equals to 1 over h squared into u x plus h comma t minus 2 u x comma t plus u x minus h comma t, and then for t we have partial squared u partial t squared is approximately equals to 1 over k squared into u x comma t plus k minus 2 u x comma t plus u x comma t minus k. So they ideally take the same structure. So call this one question 3. So that is by definition of the difference, central difference of those second order partial derivatives. So since the grids spacing is uniform along both axes, then it means that xi minus plus 1 minus xi should give us h, and xi minus xi minus 1 equals to still the same h. This is for I running from 0, 1, 2, 3, up to the last value is n, and tj plus 1 minus tj is given by k, and tj minus tj minus 1 is still k, because these are adjacent points. So where j runs from 0, 1, 2, 3, up to m. So call this one equation 4. This one, we call it equation 4. And then remember, from this equation 4 is still the same thing as saying, this one is the same as saying xi plus 1 equals to xi plus h. And this is the same thing as saying xi equals to x. So xi minus 1 . So xi minus 1. If we make it the subject, then we have xi minus h. And here we have tj plus 1 is nothing but tj plus k, and tj minus 1 is tj minus k. So this is just from these definitions here. And then next we say, so therefore we approximate, or we use the notation u sub I comma j to mean u of xi comma tj, and then so using this notation, so with this notation, so this is really what you mean, that when you see an I, you remember that it means xi, and when you see a j, you remember that it is tj. So that's what we mean by that notation. So using this notation, in 3, we have, so we can derive those partial derivatives in this form. Partial squared u partial x squared is approximately equals to 1 over h squared into, because now we had, so when we have, so remember, when we have an x general, is the same thing as just saying xi. And when we have t, is the same thing as saying tj. So remember that. So that we'll have the first term will give us u I plus 1 comma j minus 2 ui comma j plus ui minus 1 comma j. And then the second partial derivative will give us partial squared u partial t squared is approximately 1 over k squared into ui comma j plus 1 minus 2 u sub I, and then plus ui comma j minus 1. So call this one equation 5. Call this 2, call it 5. Now, so substituting 5 in 1, we get, so you're putting now this partial derivatives in terms of I and j in equation 1. So therefore, the left-hand side of 1 will give us 1 over k squared into ui sub j plus 1, and then minus 2 ui sub j plus ui comma j minus 1 equals to c squared over h squared into ui plus 1 comma j minus 2 ui comma j plus ui minus 1 comma j. And then when you multiply both sides by k, so we'll have ui comma j plus 1 equals 2 so I multiply both sides by k, so I have c squared k squared over h squared. And then so this one will be now, I'll have ui plus 1 comma j minus 2 ui comma j plus ui minus 1 comma j. And then this one will be now plus, so plus so ui sub j plus 1. So this will be minus, not plus. So some minus there. So this will be minus, minus u, or say plus, say 2 ui sub j comma j minus this one here, ui comma j minus 1, because this is the term that you have left on the left-hand side. So these are the two terms that are taken to the opposite side. So therefore, this is what we get. Call this one equation 6. All this, call it 6. So with this 6, so the initial conditions together with the boundary conditions are given in question 2 can be written in difference form. So we can write those ones in difference form as, so when you have, so remember the initial conditions were given by, so we had u0 comma t equals to f of t, and then we had u at equals to g of t, and then we had u x0 equals to phi of x, and then we had partial u partial t at x0 is given by psi of x. So therefore now with this new notation, the difference notation for this one will be u sub 0 comma j, because this general t, and remember from what I've said, t is the same as tj, and we are showing here this one by representing t by j, or tj by simple j, and x is the same as xi, and we represent it as I, equals to f of xi, f of xj, that's t is j, and then this one here will be u n comma j equals to g of tj. So remember we had the interval from x was running from 0 to a, and we are dividing it from x0, x1 up to xn. So xn is the same as a, which is the same as n in this notation. This one will be given by u sub I comma 0 equals to phi xi, and then this one will have So remember this the same as derivative is the same as change in u over change in t. So therefore, the difference between consecutive values of x values. So this is the same as saying u I comma 1 and then minus u I comma 0 equals to phi of xi. Or you can even say ui comma 2 minus ui comma 1 equals to the consecutive values of x's, consecutive values of t, because this now differentiation with respect to t. With respect to t, remember when you are carrying out partial derivative. So the same thing, so remember you can as well define it as ui 2 minus ui 1 or ui 3 equals to minus ui 2, the same thing as that phi of xi. So call these ones, call them 7. So with those, so if you have 7 with those notations as boundary conditions, then defining R for C K over H. So which means then we had C squared K squared over H squared will be given by R squared. Equation 6 becomes u I comma j plus 1 equals to R squared into u I plus 1 comma j plus u I minus 1 comma j and then plus 2 into 1 minus R squared u I j and then minus u I sub j minus 1. So replace R in the equation 6 and then simplify. You'll get this. You'll get this equation that we are writing here. So this is this is the Nicholson method of scheme for solving solving that partial differential equation. So remember, I is from 1. In this equation, you use 1, 2, 3, up to n, and j is from 1, 2, 3, up to m. So so call this one equation 8, this formula here. So if r equals to 1, then equation 8 becomes, so if you let r to be 1, so equation 8 will be u I j plus 1 equals to u I plus 1 j plus u I minus 1 j minus u I comma j minus 1. So this is the equation that you will use when you get the value of r to be 1, because the term in u I j goes to 0. So this is what this happens when r equals to 1. And then one thing that you need to remember is that when you are doing numerical solution, you need to know whether the solution is stable or unstable. And then the stability of this method is assured if and only if and only if the value of r which is the same as ck over h is less than or equals to 1. So if r is more than 1, then the method doesn't give the correct solution, and then therefore that is not the therefore the method will not give a better approximation to the solution. So just remember that equation 8, which is the Newton, which is the Crank-Nicholson scheme, is used to find the values of j plus 1th row, j plus 1th row when you are solving a partial differential equation using this method. So in the next series, we'll describe an example on how to carry out approximation of the wave equation using the using the Crank-Nicholson method. So thank you, and please watch the next video to illustrate how you can apply Formula 8.